Imagine that you are outside on a clear, starry night, stargazing. You're looking to the north when suddenly there's a magnificent shooting star to the south. You missed it. Wouldn't it be cool if you could go back in time to be looking in the right direction to see the shooting star? Okay, we know that's not possible, but what if we could build some sort of telescope that we could send back in time to be pointing in the right direction? Turns out that something like that is possible, as we recently demonstrated experimentally. Let me explain. So it turns out that there's an established connection between quantum entanglement and time travel, a mathematical equivalence, which means that if we find a way to manipulate entanglement in just the right way, we can simulate trajectories of particles that go back in time. We wondered if we could use this idea to make some kind of time-traveling detector. So let me try to explain a little bit about entanglement. This is the spooky but super powerful part of quantum physics. Entanglement can happen when two particles share a particular joint state. One example is what we call the spin singlet state. The total spin is zero, so one points up while the other points down, but it's not determined which one's pointing up and which one's pointing down. Here's what this means. If we have these two particles in the singlet state, and then I measure one particle along a particular axis, if it's spin up, then the other will be pointing down. Along a different axis, one is up and the other is down. Or maybe one is down and the other is up. No matter what direction I decide to measure, the two spins will be perfectly opposing. That's true even if the spins are very far apart, on opposite sides of the universe. Measuring one spin instantly affects the other. Einstein called this spooky action at a distance. But maybe entanglement is not so spooky after all. Maybe it's just time travel. To explain, let's first do something somewhat mathematical. Let the symbol U represent the creation of an entangled state of two particles, like the singlet state. Now let's put this symbol on a drawing of space-time, where time runs vertically and space is in the horizontal direction. This drawing represents the preparation of an entangled state at some initial time, and then shows the two entangled particles just going forward in time. If at some later time I measure the particles, I'm guaranteed to find the spins always pointing oppositely, because they're entangled. This is mathematically equivalent to the trajectory of one particle that travels backwards in time, flips sign when it turns around, and then goes forward in time. When I consider that the measurements of the two particles always have anti-correlative results, no matter how I measure them, it's because it's the very same particle. See? Not so spooky anymore. We use this connection to build a type of time-traveling detector. Now it's not a telescope, but instead it's just a single spin, the most basic kind of sensor. And here's how a spin sensor works. When it interacts with some external field, like a magnetic field, its direction can change. And then by measuring the change in its direction, we can get information about what we're trying to measure. But the problem is that if the spin is pointing in the wrong direction, it might not be affected by the field we're trying to measure. It's just like pointing a telescope in the wrong direction. We might not see anything. In both cases, we need to know what direction to point the detector in order to ensure that we can measure something. Now, inspired by the shooting star example, we wondered if we could use the time travel entanglement connection to make sure that the spin was pointing in the right direction in hindsight. So here's how the entanglement-based detector works. We first make the singlet state. One of the particles, the probe, experiences the field. Then, at some later time, we can decide to measure the other spin in a particular direction. That effectively sends the direction backwards in time, ensuring that the probe was pointing in the optimal direction for whatever we wanted to measure. Now that's pretty cool, and it's actually a demonstration of a quantum advantage. For example, let's say you wanted to measure some unknown magnetic field. If you have normal, unentangled particles, the best way to do this is to send in the spins pointing in the three different directions. But it turns out that 1/3 of the time, you'd have a spin pointing in a way that can't measure the magnetic field. So the success rate is 2 out of 3. We found a way to trap the probe in a closed, time-like curve. That is, we create the entangled state, and then we measure in the same basis. Here, when the particle interacts with the magnetic field, it gets knocked off the closed time-like curve. The probability tells us about the magnitude of the field, with 100% chance of success. So entanglement can boost our sensitivity by 50%. This kind of improvement is a big deal since it highlights the power of quantum. Our technology is still a ways from extending these ideas to real telescopes, but we don't think it's crazy impossible. So in the end, is time travel possible? No. But quantum entanglement just might be the next best thing.